redeeming characteristics, right? So there you are. Our next step is to look at organizing data. So let's look at a categorical variable. And let's say we're going to choose favorite color. And we're going to give people a choice between red, blue, and green. And I'm going to record their responses just as R, B, or G. So let's say that I'm taking my data and I get responses red, red, blue, green, blue, red, blue, blue, green, blue, red, green, green, blue, green, red. Let's see, what do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20. And we'll keep going. Yeah, well. So there we have 40 responses. Looking at these responses, just a show of hands, how many of you would say it looks like red is the most popular color? Okay, how many? A couple. How many of you would say blue is the most popular color? Nobody? How many would say green looks like the most popular color? How many of you really have no clue looking at it? Most people. Okay. It's actually a psychological fact about people that the average human can only really take in between 7 and 13 pieces of information at any given time. So if you're looking like right here, there it looks very much like red is the most popular color, doesn't it? But if you're focusing right in here, it very much looks like blue is the most popular color. And here it looks like green is the most popular color. So which one is it? Well, we're going to organize this into something we're going to call a frequency table. And in a frequency table, we have the category first. In this case, we're going to label it color. And our possible choices are red, blue, and green. And then we're going to have the frequency. But I'm going to put an extra column in here. Normally, this extra column wouldn't be in here, but I'm leaving it in here to construct this table. And I'm going to call it the tally column. What I'm going to do is I'm going to use that to tally up my results here. So I've got red, red, blue. So red, red, blue. Green, blue, red. Green, blue, red. Blue, blue, green. Blue, blue, green. Blue, red, green. Blue, red, green. Green, blue, green. Green, blue, green. Red, blue, blue. Red, blue, blue. And green, red. So we're halfway there. Red, blue, red. Red, green, blue. Blue, green, blue. Red, red, green. Red, green, green. Red, blue, red. Green, red. So looking at this now, we can see that we have 15 red responses, 13 blue, and 12 green. Now, looking at the data, many of you might not have guessed that it was going to be that close. Now, like I said, if I were actually presenting this as a frequency table, I would take this tally column out and it would just be the color and the frequency. You probably could have just counted them up, but to me it's easier to go one by one like that and cross them off and tally them up. There's also something called the relative frequency. Now, depending on, I mentioned earlier, statistics has different trains of thought and different viewpoints. Depending on what textbook you're looking at, some of them define relative frequency, bless you, and percent frequency to be different. Some of them define them to be the same thing. They really are pretty much the same thing. Define the relative or percent frequency. The first thing you have to do is find the total. Well, the total here, if we add these up, is 40. So the relative frequency, you take the frequency divided by the total. 15 divided by 40 is going to be 30.375, or 37.5%. 13 divided by 40 is going to be 0.325, or 32.5%. And 12 divided by 40 is going to be 0.3, or 30%. To be consistent, we're going to go 30.0%. Now, when you add these up, this better add up to 1.0, and this better add up to 100%. Now, they may not always be exact. It might be 0.999 or something like that, or 0.001, because there's going to be round-off errors. I mean, dividing by 40, you can come out to a precise decimal. But if you're dividing by 70, you could get a decimal that goes on forever, and you have to round it off. Now that you have this information organized like this, we can put it in a graph. One type of graph is a bar graph. A bar graph can be either vertical or horizontal. So we're going to go horizontal or vertical. In a horizontal bar graph, the categories go on the left side. And then there's a scale that goes across the bottom. We need to go up to at least 15 here. So I'm going to go by 5s. 5, 10, 15. Make it easy on myself. Now I'm going to make a bar for each of them. Red was 15, so I'm going to make that bar up to 15. Blue was 13, so that bar goes up to about 13. And green was 12, so that bar will go up to 12. Now here, since these are relatively low numbers, you can pretty much look at this and say, yeah, exactly, the red is 15, the blue is 13, and so on. But if we had larger numbers, it'd be a little bit more difficult. I'll show you an example of that in a little bit. Vertical. Do a vertical bar graph, the categories go along the bottom. Red, blue, green, and you number up the sides. So 5, 10, 15. Red goes up to 15. Blue goes up to 13. Green goes up to 12. Question for you. Does it matter what order I put these bars in? No. It doesn't matter at all. I could have put them in any order I wanted to because there is no logical order between the colors. You'll also notice that there's a space between the bars, and that's important. On a bar graph, for categorical data, there should be space between those bars. Now, one thing I did do wrong, I look back, I made this bar wider than the others. That's very poor form because it makes it look bigger than it really is. And that's one thing that you deal with statistics is bad graphs is the biggest mistake that's made in reporting statistics. Just something as subtle as that bar being slightly wider. Even though you're looking at the length, psychologically your mind is looking and saying that lens is a lot bigger. It's wider. Something that gets done a lot in these graphs. Let's say I want to compare my company to my 2 leading competitors.
One sec, did you say that the space between the bars doesn't matter or does matter?
You do have to have, since this is categorical, you must have a gap between a space between those bars.
Okay.
I believe if you're doing histograms, that's when you don't need the space.
Yep, that's exactly. When we do a histogram, you must have no space between the bars. And we'll get to that when we talk about numerical data. So we're going to compare the annual sales between these 2 companies. Like this. My company is going to look like that. Company A is going to look like that. And company B is going to be about like that. Well, if you look at this, you would say that I am really kicking butt on companies A and B here. But that's not necessarily true. Can anybody tell me why?
You have that little equal sign on the left.
That's actually not an equal.
You split it up.
Yeah. It's technically not an equal sign. It's a hash. It's a double hash. And what it is, it's a break in that number line. Notice I didn't start at 0 and label up like I did here. Here I went 0, 5, 10, 15, evenly spaced. Here I did that little break in my axis and I started numbering at 60,000. So the difference between company A and mine is only about 2,000. But it looks like I'm 3 times as much as A because of that. If this graph had been done to scale, let's put that at 10,000. Well, this is 50,000, 60,000. Starting at 0, mine would be about like that. Company A would be about like that, and company B would be about like that. Now you can still tell mine is slightly larger than theirs, but they're really, really close to the same size. This type, it's called a broken axis or a broken bar graph. It's made to emphasize the differences, exaggerate the differences. It's not that this is wrong, it's just it can be very misleading if whoever's looking at it doesn't know what they're looking for. Also, because I used big numbers here, either one of these graphs, can you tell exactly what my sales were for the year? Well, you can tell it's more than 62,000 and less than 63,000, but you couldn't give me an exact number. Graphs are not good at getting exact numbers. Graphs are good at comparing. Even over here, you can tell that mine is greater than the others and that A is the smallest of the 3. But you can't tell an exact number. If you want an exact number, you go to a table. Tables give exact numbers. Graphs give quick comparisons, visual comparisons. Another thing that I see done all the time is like I was showing you before. With the colors, even though all that matters on these bars is the height, psychologically your mind sees the size of that bar and it's going to say that one looks bigger to me. Studies have been done with color. If I have 3 bars that are exactly the same size, there have been studies done to show different orientations, whether it's horizontal or vertical, different colors, even though the bars are exactly the same size, people will pick certain colors that look like they're bigger than the others. And no, it's not always red. Another type of graph that you might make off of this would be a pie chart or a pie graph. A pie chart goes off usually off of that relative frequency or percent frequency. And if this had been back in the day, 20 years ago or so, we would have, had our circle, we would have calculated. I would have gone up here to my data and said, okay, this is 37.5%. Find 37.5% of 360 degrees, take out my protractor, measure that angle, and draw it in. Well, these days we have computer programs, Microsoft Excel being one of them, that I can put those numbers in and very quickly make a perfect circle graph or pie graph for me. So I don't have to be able to draw them by hand perfectly. But what I expect that you do know is looking at a circle graph, half the circle would be what percent? 50. Pretend I actually hit half a circle there. A quarter of a circle is going to be 25%. And if I cut that in half, that'll be about 12.5%, right? So looking up here, I have one of these that's 37.5%. That would be 25 plus 12.5, right? That'd be 37.5. That was for the red. So red is going to be that size right there. Now the other ones have to be smaller. So there's 25, 37.5. I cut that in half. The one was 32.5, which is about halfway between 25 and 37.5. That was the blue. That's a little bit more than halfway, so it's going to be something like that. There's my blue. And the rest is going to be green. And of course I should get all those other marks out of there so they're not confusing us. There we go. Now even what I did here could be considered poor form, because by using the different colors, red, blue, and green, because these are relatively close, I mean we're going from 30% to 37.5%, not a huge difference there. The difference in color could actually draw your mind to think one is bigger when it isn't. Okay. To be honest, it's almost impossible to make a perfect graph. If you made any sort of graph, no matter how careful you were, 95% of the time I would be able to look at that graph and pick apart something in it that could be deceiving. Statistics is really tough. And most of the time people are intentionally they're trying to prove their own point. They're trying to sell a product. They're trying to convince somebody of something. So most of the time people are intentionally trying to twist the statistics. But even if you're not, even if you're trying to honestly report statistics, it is really tough to try to report it without some sort of bias. At some point your personal opinion or preference comes into it, or inadvertently you do something that makes people draw someone's attention where it shouldn't be. Mark Twain once said, there are lies, there are damn lies, and then there are statistics. There's a lot of truth to that. I've done exercises where I give a set of data, and from that same set of data, I argue both sides of the same point. And I do a very good job of proving both sides of the same point from the data. Okay, we're going to look then next at numerical data. For numerical data, let's say that we are going to choose, now we're going to look at discrete data first. And we are going to choose the first variable we're going to look at is number of classes you're taking right now. So this is discrete, and it's a limited value discrete. I mean, very few students are taking more than like 6 or 7 classes. So let's say that we have students taking, in the survey we did, it's anywhere from 0 to 5. So let's say we have results, well, if they were taking 0 classes, they technically wouldn't be a student. So let's say as we're going from 1 to 5. So let's say we've got 2, 3, 1, 5, 2, 4, 3, 1, 5, 2. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good enough. 4, 1, 3, 2, 3, 5, 4, 5, 3, 2. So there are 20 students surveyed to see how many classes they're taking. So my frequency table, now I'm going to label this number of classes and frequency. I could have done a tally column here again, but this is a slightly smaller set of data. I only have 20 numbers instead of 40. So I think I'm going to do okay counting here. So I'm going to cross off 1, 2, 3 ones. There are 3 people that have 1 class. 1, 2, 3, 4, 5 twos. We have 1, 2, 3, 4, 5 students that have 3 classes. 1, 2, 3 students with 4 classes. And 1, 2, 3, 4 students with 5 classes. Just like with our categorical data, we can do a relative or percent frequency. I'm just going to say relative frequency, and we know that that can be quickly converted into a percent. Same process, we have to start out with a total. We add up the frequency column, we get a total of 20. So the relative frequency, this is going to be 3 divided by 20. So 0.15. 5 divided by 20, 0.25. The next one, still 5 divided by 20, is still 0.25. 3 divided by 20 is still 0.15. And the last one is 4 divided by 20 is 0.20. And again, that better add up to 1.00, and it does. Again, it might be 1.001 or 0.999. It has to be really, really close to 1.00. We can graph these then just like we graphed the other stuff. There are circle graphs. When we have numerical data, it is called not a bar graph, but a histogram. One thing is a histogram is always vertical. You don't do horizontal histograms. Other than that, it looks a lot like a bar graph. Along the bottom, we have our categories again, but now instead of categories, it's numbers, 1, 2, 3, 4, 5. Up the side, we have our scales. Our largest number was a 5. So we're going to go 1, 2, 3, 4, 5. So we have 3, 5, 5, 3, 4. So one class was 3. Oops, I got to go a little bit wider. It helps if I divide these up. It makes it easier on me. So there's 3 students with 1 class, 5 students with 2 classes, 5 students with 3 classes, 3 students with 4 classes, oops, and 4 students with 5 classes. Now, as I mentioned before, you can see now those bars have no space between them. In a histogram, that is intentional. The reason there's no space between them is, first of all, there is a logical order. These should go 1, 2, 3, 4, 5. Second, there is a logical link from one to the next. 2 comes after 1, 3 comes after 2, 4 comes after 5. So there is a progression. They do flow into each other. So that is very intentional that the histogram has the bars tight together. Again, it's that psychological effect so your mind can see that they do one flows into the next.
Is that just because there's numbers, both vertical and horizontal? Because there's sometimes where there's a page here in the book where it's like You know, like the temperature, that is a number, but they're talking about temperatures in the months. So is that because
Yeah.
one is numbers
Because
and the other is
what they have there is they have the month across the bottom. That's January, February, and so on. So these are categories down here, not numbers on the bottom.
Okay.
Now, and technically what you're looking at, we have temperature and month. That's a different type of graph altogether. That's what's considered a time series plot. So you're not comparing different results of a variable. You're comparing one variable and its results over different periods of time. We'll talk about that in just a little bit. So that was when we had a discrete variable and we had a very limited number of responses. We can have a large response discrete variable. A large response discrete variable might be age. We might have students that are age 17 or 16 even. We got some high school students on up to 75 or 80. We can't list out every age, every year. Or if it's, so that would be discrete. Because we're looking at, now obviously time is not discrete, it's continuous, but I'm asking for your age in years, so I'm defining it in such a way that it's discrete. You're going to count the years you've been alive. Or if you're looking at continuous, like height. Well, there's people that are 5'9", there's people 5'10", but there's people 5'9" and a quarter, 5'9" and 3/4. You can't list out every possible height. So what you're going to do is you're going to divide it into classes. You're going to create classes, which are basically ranges. So what we're going to look at is scores on a test. And you really can't possibly list out every possible score on a test. And to save time, because I'm getting long-winded here tonight, I'm not going to list out the raw data and construct the frequency distribution. I'm just going to give you the frequency distribution. So the first column, I'm going to label it score or classes or class. And then frequency again. And let's say that on this particular test, nobody scored below a 60. So I've got 60 to 69, 70 to 79, 80 to 89, and 90 to 99. Now somebody might ask, why don't I make that last one 90 to 100 in case somebody had a perfect score? These classes, these ranges must be exactly the same size. If somebody had a perfect score of 100, I'd have to adjust them. I might do 61 to 70, 71 to 80, 81 to 90, 91 to 100. They must be exactly the same size. Now, if I was looking at like people's heights, we have to look at how we measure it. If we're just measuring to the nearest inch, well, that's one thing. Then we could just go, maybe 60 to 64 inches, 65 to 69 or whatever. If we're measuring to the nearest tenth of an inch, you'd have to go 60 to 64.9 and 65 to 69.9 and so on. You have to make sure that there isn't room that something could fall in between classes. So if you're measuring to the 10th, you have to have your classes down to the 10th. Let's just say our frequency here, we had 2 people in the 60 to 69. We had 8 people in the 70 to 79. We had 7 in the 80 to 89 and 3 in the 90 to 99 range. There is our frequency table. And we could make a histogram the same way. We have our ranges down here, 60 to 69, 70 to 79, and so on. I'm not going to finish that off because you get the picture. We're going to have the bars. 2, 4, 6, 8. I'm labeling by 2s. This is going to be 2, 8, 7, 3. So we can organize our data in those frequency tables and use that frequency table to create our graphs. Any questions so far? Now the last type of graph is the one you mentioned. What we were looking at here, we're looking at a snapshot. This is all information that is gathered at a single moment in time. And we're allowing it to put that single measurement and looking at how we're measuring that value for several different elements and comparing those values to each other, describing those values. There's something else called time series. And in time series data, we're only looking at one element and one measurement of that element and looking at how it changes over time. Now, the one you brought up was temperature. We might have the day's temperature. Might label the day of the month, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. Now, even though these happen to be numbers across the bottom, they are representing days of the month, so it's not really numerical data. The response is actually what's going to be along the left side here. Let's say that the coldest it's been was 30 degrees. And we're going to go up to 70 degrees here. Generally, this is going to be a line plot, although I have seen it done with bars. Generally do a line plot. So let's say that on the 1st of the month, the high temperature was 48. And on the 2nd, it got up to 52. On the 3rd, it only got up to 43. On the 4th, it got up to 59. The 5th, it got up to 58. The 6th, it got up to 61. The 7th, it was back down to 51. And on the 8th, it was at 54. Now again, just like with the bar graphs and the histograms, if I wanted to know the exact temperature on any given day, it'd be really hard to get that exact temperature off of this line graph. But what I can get really quickly is when was the temperature increasing? From day 1 from the 1st to the 2nd it increased, 3rd to the 4th, 5th to the 6th, 7th to 8th it increased. The other spots it was decreasing. Where is it increasing the fastest? Well, right here the line is the steepest. That's where it increased the most or the fastest. So the line plot gives us those things. Increasing, decreasing, how fast is it increasing or decreasing? Okay. So enough about visual displays. Time to get into crunching the numbers. And to talk about crunching numbers, we have to talk about something called a data distribution. So let's look at these test scores again. We said that we didn't have any scores less than 60. So I'm going to create a number line. Pretend these are evenly spaced. For some reason they're getting closer together as I go, but don't claim to be an artist. So we're going from 60 up to 100. So that covers at least the range of our data. And now we're going to take the test scores and we're going to put them on this number line. Pretend that line is straight too. Holy cow, is that crooked. Anyway, so let's say the first test scored an 81. So we're going to put a dot above the 81. This is what we call a dot plot, by the way. The second one's a 76. We put a dot at the 76. Then there was an 89 and an 84. Another 81. So we put a dot above the original dot if there's already a dot there. 79, an 80, another 81, an 82, an 86, a 93. And we keep putting dots on here as we read scores. And what we see over time is these dots build up and they start to form a shape. And the shape of this is the data distribution. Now, most of the time, as these dots build up, they're going to form a shape that looks something like this. You've heard it called the bell curve. Exactly. The technical name for that bell curve is a normal curve. The reason it's called a normal curve is that is the shape that data in nature normally takes. If you look at the height of people, it forms approximately a bell curve. Most, you look at your, they call them norm reference tests. Those are normal reference tests. Most of your high-end tests, like your ACT and stuff like that, you put the people's scores on there, would form a bell curve. So, about this curve, we need to be able to describe a couple of different things. One is the center of the curve. So we've got that curve there. Let's say we have a second curve here. This green curve, let's say the green curve represents the test scores for another instructor's class. Well, how would you describe the difference between those two curves? Well, the center of the green curve is less than the center of the blue curve. The second quality that we describe about them is the quality of spread. Now, the blue curve and the green curve here are equally spread out. They have the same width. So if I bring in another curve, comparing the purple curve to the blue curve, they have the same center, but the purple curve is narrower. It is less spread out. The blue curve is more spread out. So we need to come up with numerical ways of describing both the center and the spread. Now, not all data is perfectly normal. Most of what we deal with is something called approximately normal. Many times our normal curve is stretched out in one direction or another. This one looks like it's leaning a little bit, and this one's going to as well. If you looked at these curves, this one is stretched out to the left. So this one is what they call skewed left. This one is stretched out on the right side, so that's what they call skewed to the right. Because of that fact that most data is slightly imperfect, we have different ways of measuring the center and different ways of measuring the spread, and they all turn out to be slightly different. If our data is perfectly normal, gives us that perfect bell curve like we have here for these, well then all of our measures of center and spread are going to give us the same result. So let's start out at looking at our measures of center. So I'm going to put a small data set over here. I'm going to put 8 numbers in. Well, I'm just going to put 5 numbers in it. There. So there's my data set that I'm going to use here. The first measure of center I'm going to talk about is the mean. the mean is what we have all referred to since about second grade as the average. How do you find the average? Add them up, divide by however many are there. The technical symbol, this little symbol here is called the summation symbol. So you do that with X, that means add up all the values, and remember is the number of items in the list, you divide by how many are there. So for this set, n equals what? How many numbers are in there? 5. Perfect. N equals 5. So we are going to add these numbers up. 16 plus 7 is 23, plus 15 is 38, plus 11 is 49, plus 28 is 77, divided by 5. Which is going to give us 15.4 is our mean. If you're doing this on a calculator, a bit of advice. You're going to be punching these in to add them up. 16 plus 7 plus 15 plus 11 plus 28. Before you hit divided by 5, hit equals. Otherwise, you remember our order of operations from the first unit, you hit divided by 5 and it's going to divide the 28 by 5 and then add that to the rest of them. So make sure you hit equals before you hit divide. Our second measure of center is the median. Our median is the middle number. To find the median, we have to do a couple of things. The first one we have to put the numbers in order. We're going to put them in order from smallest to largest. So that's going to be 7, 11, 15, 16, and 28. Now, this is a really small set of numbers, so I can just look at them and I can see what the middle number is. I can see that the 15 is in the middle. But if it's a larger set of numbers, I would go through finding the position of the median. The way I find the position of the median, it is n times 1/2, or n times 0.5. The median is the middle, which means half of the data is below it, half of the data is above it. So what I'm actually calculating here is how many data points are below the median. There are two possibilities. N is odd, which is the case we have right here. So for this one, n equals 5. So the position is going to be found by doing 5 times 1/2, or 0.5. I'm going to do 0.5, which is going to give us 2.5. That is a decimal. We're going to round up to the third position. So 1, 2, 3, that's my median. So 15 is the median of this set of data. Now I'm going to give you another set of data just for finding the median. This set of data, n is going to be even. So that's our second possibility, n is even. So I'm going to give you a set of data for that. I'm going to put them in order from smallest to largest right now, but normally that's still going to be the first step you have to do, is put them in order from smallest to largest. I'm just going to put them in order right now to save time. So I've got 12, 19, 23, 24, 31, and 39. So now in this case, n equals 6. So my position is found by doing 6 times 0.5, which is going to equal 3. Since that come out to be a whole number, the position is between that position and the next, the third and the fourth position here. So we've got 1, 2, 3, 4. The median is between 23 and 24. How do I find what's in between them? Add them together, divide by 2. 23.5. So for that data set, the median would be 23.5. I put that one in a different color because the 15 and the 15.4 are describing the same set of numbers. That one's a different set. You'll see here the mean and the median are relatively close for these two sets of numbers. They're not exactly perfect, but they're close. There is a third measure of center. Called the mode. The mode is the number that occurs most often. The two data sets I gave you here, neither one of them has a mode because there's no numbers in either data set that occurs more than once. The mode is really only useful in really large data sets. If I have a lot of numbers, then the mode becomes useful. In a small data set, the mode is kind of pointless. So now the question becomes, there's actually a third one I'll throw out here, or a fourth one I'll throw out here just for that. There's a fourth one called the mid-range. The mid-range is found by taking, come on, the minimum number, the smallest number, and the largest number, the maximum, and averaging those two together. It's really the middle of the range. So if I was looking at this set here, 12 plus 39 divided by 2. So that'd be 51 divided by 2, which is 25.5. The mid-range is not a very good measure of center. You see it came out to be pretty different from the median for that set. Now, like I said, oops, go ahead.
So what would be the purpose of even using mid-range?
Well, if we have a good data set, a data set that is normally really, really close to being normally distributed, a perfect bell curve, all four of these measures of center will be exactly the same. So if we know our data is really, really close to being a bell curve, then the mid-range is just a really quick way of finding the center. So now the question comes out, which is best? Now there's always a few people that argue that either the mode or the mid-range is the best because they're really easy to find. Well, you can obviously tell by the way I worded that what my opinion is. Usually it comes down to the mean or the median. A lot of people say the mean is the best because, well, one, they've been doing it since like second or third grade, averaging them together, adding them up and dividing. And it feels like it's very mathematical. We're doing math. We're adding and we're dividing. Where the median, you're just finding a position and locating that number. But let's look at an example here. I'm going to give you a set of numbers. Once again, I'm going to put them in order from smallest to largest. So in this set of numbers, 5, 10, 11, 13, 21, the mean is found by adding them up. So 5 plus 10 is 15, plus 11 is 26, plus 13 is 39, plus 21 is 60. 60 divided by 5 gives me 12. So I have a mean of 12. The median, well, you can look at the set and tell me what the middle number is. What is it? 11. Again, that only works because it already put the numbers in order from smallest to largest. So the mean and the median are relatively close there. Now I'm going to create a new data set. Should be looking a little bit familiar at this point. And not so familiar now. All I did is added 1 point to that data set. The mean, if I add those numbers up right now, that new total is 120, and there's now 6 numbers there to divide by. That mean is now 20. The median is going to be between these two numbers. Between 11 and 12, or 11 and 13, I should say. 11 plus 13 divided by 2 gives me 12. You can see here the mean, because of that one really large value, we call that an extreme value, the mean jumped from 12 up to 20. The median only went from 11 to 12. The median is what we call more stable. It doesn't change as much when we have extreme values, either really large or really small values. Because of that, statistically, we consider the median to be a better number. That's why when you see federal studies, they talk about median income level and stuff like that, median debt levels, because there's always that one person that's way off the charts. I'm going to give you, I know I'm a couple minutes late on break here, and I'm just going to give you one example, and then I'll let you go on break. In 1983, University of Virginia advertised that the average starting salary for somebody with a 4-year marketing degree from their school that year was just over $78,000 a year. Put this in perspective, in 1983, the average high school teacher was coming out of college starting out at about $16,000 to $18,000 a year. $78,000 a year was really good starting salary. In fact, for $78,000 a year, I might be tempted to leave here. What they did not disclose was that one of those graduates, and he did graduate from the marketing program with a marketing degree, was a man by the name of Ralph Sampson. Now, most of you are probably too young to remember Mr. Sampson, but I remember Mr. Sampson. Mr. Sampson was 7 foot 4 inches tall, was the 2-time NCAA Basketball Player of the Year, and was drafted #1 by the Houston Rockets. He signed a multi-million-dollar contract, but he graduated from the marketing program. It takes a lot of $20,000 a year marketing graduates to average out a multi-million-dollar contract to $78,000. He was the only person in that graduating class that made more than $33,000 that year. The median, that obviously was the mean. The median was around 24,000. I don't remember the exact number, but it was between 24 and 25,000 that year. Yeah, about a third. If you took out Mr. Sampson's pay, both the mean and median were in the low 24,000. But with his in there, that one extreme value, because the mean is so sensitive, it shot way up. Okay, we're about 5 minutes late for our break, so let's go ahead and take our break. We'll come back in about 7:35.